Hello, dear engineers and technocrats. I welcome you all to your favorite YouTube channel, Industrial Engineering Guru. Please like it, share it, and give feedback through writing comments. After completing today's session, you will be able to define and plot an operating characteristics curve. You will also be able to explain the importance of OC curve. You will be able to define average quality level, lot tolerance, percent defective, producers risk, as well as consumers risk. This session will enable you to describe the impact of several sampling parameters on the shape of an OC curve. In previous session, we defined acceptance sampling. It is a process in which we take a sample from a population or a production lot. The items in sample are selected randomly from the lot so that they are representative of this lot. Now we carry out 100% inspection of these items in the sample for all requisite quality characteristics. And based upon this sample inspection, we decide whether to accept this lot or reject it. So this is the process of acceptance sampling. In doing so, we can take a single sample or we can take more than one sample. So depending on the number of samples, the acceptance sampling plans can be categorized as single sampling plan, double sampling plan, multiple sampling plan, and sequential sampling plan. We defined these plans in previous session, and you know that there are few parameters which are used to define these plans. Now for a given situation, which type of sampling plan is the most suitable? In order to find this, we have to evaluate these plans on some criteria. So the effectiveness of sampling plans is measured based on mainly two criteria. One is its discrimination power and another one is the cost of carrying out this plan. We use these four types of sampling curves to measure the effectiveness of sampling plan. First one is operating characteristic curve. Second is average outgoing quality curve. Third one is average sample size curve. And fourth one is average total inspection curve. So these four curves are basically used to measure the effectiveness of sampling plans. And after measuring the effectiveness of each plan, we decide which type of plan is more suitable under a given condition. In today's session, our focus will be on operating characteristics curve, popularly known as OC curve. In subsequent sessions, we will take up the remaining curves. Now we will discuss if a sampling plan is given, then from this plan how we can plot an OC curve. You know, OC curve is a plot between probability of accepting a lot and proportion of defectives in the lot. So a sampling plan, single sampling plan where lot size is 500, sample size is 12 and accepted number is 2. So from a lot of size 500, 12 items are randomly selected and they are thoroughly inspected, and lot is accepted if the number of defectives found in this sample is at most 2. So we use here hypergeometric distribution and we assume that lot contains 5% fraction defectives. 5% fraction defectives means if the lot size is 100, there are 5 defectives. So in lot of size equal to 500, it will consist 25 defectives. Now probability that the sample of size 12 items contains 0 defective is given by this hypergeometric distribution function, where capital N is the sample size, D is the maximum defectives in this lot, that is we obtain by multiplying this lot size N and fraction defectives 0.05. N, small n is your sample size and D is the number of defectives found in sample. So we put the values in this formula. So this 500 minus 25 gives 475. N is the sample size and if D is 0, we get 12. This capital D is the number of defectives in lot, that is 25. We determine by multiplying lot size 500 and this fraction defective 0.05. So The probability that sample contains zero defective is 0.5366. Similarly, we determine the probability that the sample contains one defective, and that comes out 0.3469. Similarly, the probability that sample contains two defectives comes out 0.0982. So probability that sample contains at most two defectives. 2 is your acceptance number as given in your single sampling plan. So we need to determine the probability that the sample contains at most two defectives is the sum of probabilities that there is zero defective, there is one defective, and there are two defectives. And this gives that there is a probability that defectives are less than and equal to 2, or probability that sample contains at most two defective, and it comes out 0.9820. So the probability of accepting the lot with 5% fraction defective is 0.9820, and the probability of rejecting the lot is 1 minus probability of acceptance, that is 0.0180. So this was the sample calculation, and we perform these calculations for varying level of fraction defectives in the lot. So this column gives decreasing lot quality, or we can say increasing fraction defectives, and corresponding to this fraction defectives, when we multiply these proportion defectives with lot size capital N, we get number of defectives in the lot, present in the lot, and this is the probability of finding zero defective, in the sample. This is the probability of finding one defective in the sample corresponding to different proportion of defectives, and this is the probability of finding two defectives in the sample. When we add these probabilities corresponding to each level of fraction defectives, we get the probability of acceptance. And you can observe that probability of acceptance decreases as the lot quality deteriorates or fraction defectives increases, and the complementary to probability of acceptance is probability of rejection. When we plot a curve between probability of acceptance and proportion of defective items, or we call it as lot quality, we get an OC curve. So OC curve is basically a curve between probability of acceptance, a lot, and proportion of defectives in the lot. It shows probability of acceptance on y-axis and proportion of defective items or lot quality on x-axis, and probability of acceptance decreases with increase in proportion defectives. Now this curve is used to measure the effectiveness of a sampling plan by showing its discriminating power between a good and a bad lot. Now when the fraction defectives are less, the probability of acceptance should be high. When the proportion of defectives or lot quality is bad, the probability of acceptance should be low. So what we mean by discrimination power, that the OC curve of the sampling plan should be such that it should have very high probability of acceptance for good quality lot, and it should have low probability of acceptance for bad lot quality. And if it is showing low probability of acceptance for a good quality lot and a high probability of acceptance for a bad quality lot, then we have to redesign a sampling plan. That is, we have to vary the sampling parameters such as lot size, sample size and acceptance number so that its discriminating power can be improved. So in subsequent slides we will discuss how we can improve the discriminating power of a sampling plan. Now here the sampling plan given was that lot size was 500, sample size was 12 and acceptance number was 2. Now for this, a very good quality lot has very high probability of acceptance, but a lot consisting about 19% defective has 60% probability of acceptance. So the discrimination power of this sampling plan is not well, because when it is not able to restrict the probability of acceptance at low value when lot quality is bad. If you like today's discussion so far, please hit the like button, share it with your friends and subscribe your YouTube channel Industrial Engineering Guru if you have not subscribed it yet. Now in OC curve, two levels of lot quality are important for us. First quality level is called, which is of interest, is called acceptable quality level. When a producer supplies a lot to the consumer based on a suitable acceptance sampling plan, the consumer makes the decision about the acceptance or rejection of lot. In doing so, the consumer is willing to accept the lot with a small percentage of defectives. This is called acceptable quality level, AQL. AQL is generally taken in the order of 3 to 5%. AQL should be set based on the criticality of the quality characteristics. More critical is the quality characteristics. The smaller should be the average quality level. For example, if a consumer is buying washers from supplier, then this washer can have two type of quality characteristics. One can be a scratch on it and another one can be a crack on it. Now scratches are less critical than cracks on washer. So AQL value for cracks should be smaller than AQL value for scratches. In acceptance sampling, second important lot quality level is lot tolerance percent defective, or we say rejectable quality level. Here consumer will tolerate a few more defects above average quality level. However, when the number of defects reaches a threshold level beyond which consumer will not tolerate them. This poorest level of quality that consumer is willing to accept is called lot tolerance percent defective, or LTPD, or rejectable quality level RQL. In nutshell, a consumer wants quality level to be better than AQL, but he may also live with quality level up to LTPD. He cannot accept any lot with a defective greater than LTPD value. Now the probability of acceptance is 100% when the lot does not contain defectives more than average quality level. Otherwise it is 0. So we know that OC curve is a plot between probability of acceptance and lot quality. Now if the lot quality is equal to AQL or less than this, it means we have a better quality lot, then it has probability of acceptance equal to 100%. And if the quality is poor than AQL, it has 0 probability of acceptance. So this vertical line at AQL showing 100% probability of acceptance is known as ideal sampling plan or ideal OC curve, and it has a perfect discriminating power between a good and bad lot. A lot is considered to be good when quality level or fraction defectives are less than and equal to AQL, and such a lot has 100% probability of acceptance. If the quality is bad and fraction of defectives are more than AQL, it has zero probability of acceptance. So such a curve is called ideal OC curve. But in acceptance sampling, we cannot have such an ideal OC. In acceptance sampling, both consumer and producer have certain amount of risk. There is a certain amount of risk for consumer in accepting a bad quality lot, having defectives equal to lot tolerant percent defective value. This risk is denoted by beta and called consumer's risk. Now let's try to understand how it can happen. When a bad quality lot is submitted by the supplier, from this lot a sample is taken by the consumer in which by chance more good items are selected, and obviously defectives found to be less than the acceptance number. Although submitted lot was of bad quality, but items selected in sample were found to be good. As a result, consumer accept this bad quality lot supplied by the supplier. Hence, the probability of accepting a bad quality lot by the consumer is known as consumer's risk. There is also a certain amount of risk for the producer in rejecting a good lot having defectives equal to AQL value. This risk is denoted by alpha and called producer's risk. This can happen when a good quality lot having defectives equal to or less than AQL value is submitted to the consumer when consumer selects item in a sample and by chance most of the defectives present in the lot comes into the selected sample. When the sample is inspected, obviously it will contain more defectives than acceptance number. So based on this sample inspection, consumer rejects the entire lot Although it was a good lot, hence probability of rejecting a good quality lot is called producer's risk. Now a sampling plan is designed in such a way that producer's risk should be less than 5% and consumer's risk should be less than 10%. The producer's risk is also called type first error and consumer's risk is called type second error. So in nutshell, we can say that based upon sample inspection, either a good quality lot is rejected, called as producer's risk, or a bad quality lot is accepted and known as consumer's risk. Now, these two values of producer's risk and consumer's risk can be calculated using this OC curve. And this value of risk will depend upon the shape of the OC curve, and the shape of this OC curve will depend upon sampling parameters such as sample size and acceptance number. So while designing this sampling plan, we should select appropriate value of sampling size and acceptance number so that producer's risk is below 5% and consumer's risk is below 10%. Here you see for this given sampling plan where lot size was 500, sample size was 12 and acceptance number was 2. Here a lot having around 7% defectives has producer's risk 5%. But a lot containing defectives equal to LTPD has very high probability of acceptance, and it is between 50 and 60%. So we see that in this sampling plan, consumer's risk is very high, and this sampling plan need to be revised so that it should not have producer's risk more than 5% and consumer's risk more than 10%. Sampling plans are usually designed to have producer's risk of 5% and a consumer's risk of 10%. And a sampling plan has perfect discriminating power if probability of rejection is not more than 5% at AQL value and probability of acceptance is at most 10% at lot tolerance percent defective or RQL value. We obtained this OC curve for a single sampling plan where lot size was 500, size was 12 and acceptance number was 2. Here you see that a good quality lot has high probability of acceptance or producer risk alpha is low, whereas consumer's risk beta is very high because probability of accepting the lot is around more than 50%. So this OC curve shows the probability of accepting a bad lot is quite high, and we can say it is biased to the producer, or such an acceptance sampling plan would not be acceptable to consumer, as consumer's risk is quite high in such a sampling plan. Now, how we can improve the effectiveness of this sampling plan, or we can say in order to improve the discriminating power of a sampling plan, let's discuss how the parameters of sampling plan affects the construct or shape of this sampling. We discussed this ideal OC curve and we noted that steeper is the OC curve, the better is its discriminating power between a good and a bad lot. An OC curve has 100% probability of acceptance when quality level is below AQL, and when proportion or defectives are above AQL, it has 0 probability of acceptance. Now you will notice that parameters of a sampling plan have significant influence on the shape of the OC curve and its discriminating power. Here you see the OC curve becomes steeper as acceptance number C decreases. Here C acceptance number value is 0, here it is 1, 2 and 3. So now we decrease the acceptance number, it becomes steeper. As far as consumer's risk is concerned, so consumer's risk beta is the probability of accepting a bad quality lot. So if we consider 20% defective as LTPD value, then you see that here it has probability below the 10%. In this case it comes out around 25%, and when the acceptance number increases, consumer's risk is increasing. So as far as consumer risk is concerned, the discriminating power of an OC curve improves with decrease in acceptance number, as it provides better protection against a bad quality lot. However, the probability of accepting a good quality lot submitted by the producer decreases with decrease in acceptance number. When acceptance number is 3, here we have probability of acceptance is equal to 100% when AQL value is 0.05. Whereas when acceptance number C is equal to 0, the probability of acceptance is between 50 and 60%. So by observing these OC curves with varying value of acceptance number, we see that OC curve becomes steeper when its discrimination power improves as far as consumer is concerned, but its discriminating power decreases as far as producer is concerned. So by increasing acceptance number, the producer risk increases whereas consumer risk decreases. When we vary the sample size value, the OC curve becomes steeper as sample size n increases. So here for this OC curve, sample size is equal to 5, here it is 12 and here it is 30. So as sample size increases, curve becomes more steeper. So its discriminating power as far as consumer is concerned, discriminating power of OC curve improves with increase in sample size. On the other hand, the discriminating power of OC curve decreases from producer's point of view. As you see that number of items taken in sample increases, the probability of rejection of a good quality lot increases, or you can say that producer's risk increases as sample size increases. So we note that when acceptance number is decreased and sample size is increased, consumers' risk decreases, whereas the effect of varying lot size is insignificant on the shape of the OC curve. Here we vary the value of lot size from 100 to 500, keeping sample size and acceptance number constant. We see there that the shape of the OC curve does not change much. So we can say that the lot size have a very little impact on the construct of the OC curve. Now, so far discussion led us to conclude that consumer risk would decrease with increase in sample size and decrease in acceptance number. On the other hand, producer's risk decreases with decrease in sample size and increase in acceptance number. So you noted that consumer prefers large sample size and small acceptance number, whereas producer prefers small sample size and large acceptance number. As consumers' risk would decrease with increase in sample size or decrease in acceptance number, whereas producers' risk would decrease with decrease in sample size and increase in acceptance number. So both consumer and producer have conflicting interest as far as sampling parameters are concerned. A sampling plan must be designed to satisfy both producer and consumer. The sampling plan is considered to have perfect discriminating power and will be acceptable to both producer and consumer if probability of rejection is not more than 5% at acceptable quality level AQL and probability of acceptance is at most 10% at LTPD or RQL level. If you like today's session, please hit the like button, share it with your friends and subscribe your favorite YouTube channel Industrial Engineering Guru. Thank you for patience hearing.